Good evening, everyone. My name is Ted Kesik, and I'm a faculty member here at the Daniels Faculty of Architecture, Landscape and Design, University of Toronto. And it's my privilege to serve as the coordinator of the 2015-16 Building Ecology, Science and Technology Lecture Series. The B.E.S.T lecture series is entering its 7th year at the faculty, and that's largely thanks to the generous support of Tremco Roofing and Maintenance. This unique lecture series focuses on specialized topics of interest to the design profession by inviting leading researchers and practitioners to share their perspectives on the emerging intersection between ecology, science, and technology in the built environment. Before we continue with tonight's lecture, I'd like to call upon John Campbell from Tremco to personally welcome everyone. John?
Thanks very much. I was sitting in the other room quietly watching Ted on the screen and wondering, wow, I wonder where he is. He's next door. So anyway, there's a few seats left over there. But thanks very much. We really are very proud to have sponsored the B.E.S.T lecture series for now, I think, 6 or 7 years. I've been working with Tremco now for 25 years in the downtown core of Toronto, and we have our largest worldwide manufacturing facility here in Leaside. We're very proud of that. We're a zero landfill manufacturer, which certainly took a lot of effort to achieve, and we're very, very proud of that. We produce high-performance roof systems, of which are very suitable, for instance, under green roofs or vegetated roofs. When you go to the effort of installing these types of systems, you certainly don't want to have a leak or deal with water issues down the road. So thank you very much. And then there's an open invitation for anybody that's interested, for instance, in plant tours. Certainly feel free to contact us, and we'd be happy to take you around and show you our facilities. Thanks.
Thanks very much, John. For those of you who wish to obtain OAA continuing education credits, we ask that you fill out a coupon and return it to one of our staff so that a certificate of participation can be issued to you. Of course, that's dependent on how neatly you print as to whether you'll ever get it. It's particularly the email address that has to be printed neatly. We can always alter the name in case it's incorrectly entered on the certificate, but if we can't email it to you, you'll never know about that. So, okay, do your best. I know nobody does drafting anymore. Anybody here? No? Yeah. Well, I used to way back when. Okay, in this 7th year of the B.E.S.T lecture series, 7 is indeed a lucky number. Working with Tremco, I am pleased to report that this year, a B.E.S.T lecture series was successfully launched at École d'Architecture, Université de Montréal, and another is also being planned to begin this coming fall at the Illinois Institute of Technology School of Architecture in Chicago. So the B.E.S.T lecture franchise is growing both in size and popularity. And thanks again to Tremco, and especially to Paul Sheehy, Vice President Sales for North America. He's really been pushing this idea of getting good information out to design professionals so they can make informed choices. Now, I would like to introduce our speaker for this evening's lecture. Liat Margolis is a professor of landscape architecture here at the John H. Daniels Faculty of Architecture, Landscape and Design, and she is also the director of the Green Roof Innovation Testing Laboratory, which we affectionately refer to as the GRIT Lab, a research facility that is dedicated to evaluating and optimizing the environmental performance of green building technologies. The GRIT Lab is recognized as a leading test facility in North America and was awarded the 2013 American Society of Landscape Architects Excellence Award in Research. Liat's hard work and perseverance, combined with the generous support of companies like Tremco, have made this amazing testing facility possible and has afforded an invaluable opportunity to discover and share what works and what does not work for green roofs in the Toronto climate region. This facility is a reflection of the dedication and creativity of its creator, its steward, and now our speaker for this evening. Please join me in welcoming Professor Liat Margolis.
Thanks, Ted, for a kind introduction and for your mentorship and support over the years. And thank you, Tremco, for your environmental leadership at large and also for your valuable support to the Grit Lab over the last 5 years. My presentation today focuses on the research activity at the Grit Lab. But before I delve into the details, I wanted to begin with just some overall questions that set the kind of framework for the research that we're doing, the kind of vision that we have for the research in the lab. And the questions that are in my mind as we grow this research initiative have to do with asking ourselves, what is the role of design or designers in advancing both knowledge and performance benchmarks of green technologies? What forms of practice and research in the professional and academic spheres allow for design or designers to engage with technological development and environmental performance testing and optimization? And given that academic institutions are among the largest and single landowners in cities, how can scholars work with the university to strengthen sustainability practices in campus planning and operations? And I look at a few inspirations as examples of these models. For example, the firm Karen Timberlake has managed to integrate research as part of their design practice. They have positioned research as an integral part of their firm. And in an article that was written about them titled "Evolving the Role of an Architect," the author writes, "The scope of the architect is elastic and expansive, beginning with the questioning and researching the very way buildings are conceived, designed, constructed, and delivered, and continuing through to material and product development and the ongoing study of management of buildings and places." And these are the kind of questions that they are taking on as a professional practice, in which, for example, they've designed a life cycle assessment tool titled Tally, which quantifies embodied energy along with other environmental impacts and emissions to land, air, and water. And with a number of scientists and ecologists on staff, the office also revisits many of their constructed projects to document plant succession and compare the original plant composition and how it has evolved and changed over time. Other projects that I've looked at, for instance, at UBC, which have a sustainability mandate, a campus-wide sustainability mandate, to look at interdepartmental research collaboratives with partnerships across private and public sectors to monitor environmental performance, with a physical building functioning as a living lab to test environmental and social performance in situ. And mind you, this building has integrated about 3,000 sensors in it. So for instance, one of the research areas among several others is intended to characterize the pervasive difference between design intention and actual performance with high-performance sustainable buildings. And within each research area, an interdisciplinary team brings a range of perspectives to assessing complex systems. So as the architectural disciplines embrace more evidence-based strategies, I believe that design professionals and academics now have the responsibility to engage in performative research and to contribute directly to the development and optimization of environmental technologies. We need to focus particularly on how these new technologies actually work and how they inform the design process. And since most sites can be equipped with sensor devices, we now have the capacity to integrate sensor technology and to derive quantitative data in real time and actually assess the effectiveness of the kind of technologies that we integrate into our green buildings. So as an overarching kind of set of objectives for the Grit Lab, we're looking at empirical data-driven research, interdisciplinary research, partnerships, education and training, and public outreach. With respect to empirical data research, we look at evidence-based research of current green technologies and standards, as well as common design practices to validate and optimize environmental performance relative to local climate and ecological conditions. We are interested in the use of sensor technologies to measure performance, and our setup is a kind of modular experimental setup whereby we can continue to integrate and explore new technologies as more come onto the market. Our current setup is actually on the 5th floor of this building. It includes an extensive green roof, research, 33 test beds, a green facade research, and also an integrated green roof and solar photovoltaic experiment. The extensive green roof research began in 2011 and looks at 4 performance criteria. We're looking at stormwater management, thermal cooling, plant growth biodiversity, and species habitat. Each bed is equipped with a number of different sensors that could measure temperature, soil moisture, and runoff. And the results from each bed is then compared to climate conditions that we record via the weather station, solar, precipitation, humidity, wind speed, and so on. The next research area that we focus on is green facades, and in particular, we look at the thermal cooling potential of green facades on building envelopes. And actually, here you can see our weather station. And in this picture, you can see the surface temperatures that are mounted to the surface of the building, comparing vegetated surfaces and a control non-vegetated surfaces, and looking at the thermal cooling potential of vining plants on the facade. And our most recent setup looks at the combination of green roofs and solar photovoltaics, with the questions about the effect of temperature and cooling via plants and evapotranspiration on energy production. We also are looking at the effects of shading on plant growth and the combination of energy and stormwater management, thus providing a new research or implementation potential in the field, looking at 2 industries that are currently competing for the same roof area, and looking at whether they have the potential to actually be combined together and work in synergy. The setup is also equipped with a number of different sensors recording ambient temperature, surface temperature of the PVs, wind sensors to look at microclimate conditions around the setup, soil moisture sensors, rain gauges to look at runoff quantities, and as well as an energy monitoring system to look at energy production. And overall, this is what our data acquisition system looks at, with over 500 sensors and data loggers recording data every 5 minutes. In terms of our interdisciplinary research, we are looking to understand complex systems from a number of different perspectives concurrently, identify the overlap, synergies, as well as contradictions in order to offer a more precise and nuanced approach to design and implementation, compare and learn from distinct disciplinary perspective, priorities, and research methods. And so our research team unites the fields of landscape architecture, building science, environmental engineering, and biology, with a number of different expertise, ranging from plant ecology to urban bees to low impact development, subsurface hydrology, and so on. Partnerships for us are extremely important. We look at the GRIT Lab as a mediator between researchers, designers, manufacturers, and policy legislators. We partner with industry and government to really understand what are the kind of practical concerns and implications in the field and make sure to align them with our research objectives. We then communicate research findings and recommendations to scholars, design professionals, industry, and policy decision makers to improve standards. So we've been very fortunate to have support from a number of different industry partners, as well as the University of Toronto Facilities and Services, the Sustainability Office, and the City of Toronto. And our research is supported by a number of different government grants. In terms of education and training, we look at this as an opportunity to really infiltrate down into the educational curricula here. We are take advantage of the kind of collaborative and interdisciplinary framework for our research students to integrate and collaborate with one another, cultivate a critical approach towards the application of green technologies, and provide with internships with industrial partners. And so our students who have been working with us collaborate with one another and learn from each other's perspectives and expertise. And we also use the Roofscape for course lectures, both at the Daniels faculty and beyond. And our last objective is really to look at this as a kind of model for demonstration, for public outreach. Usually during the summers, we host a number of different tours. For instance, last year we hosted Doors Open Toronto with over 200 people who visited us. We also make all of our drawings and findings and publications available online. And we have a new tool that we have developed which actually shows the green roof beds in comparison to one another and in relationship to various testing variables where you can look at them, how they've changed over time and over the duration of the study. So far it's been 5 years, and that's available online. So what I'd like to do is share with you our preliminary green roof research findings. First, a bit of background on how the experiment was set up and why. As you may know, Toronto launched its green roof bylaw in 2009, which mandates the construction of green roofs, extensive green roofs, which are of depth up to 15 centimeters on all new residential, commercial, and industrial construction with a minimum square footage of 2,000 square meters. And along with that bylaw comes a construction standard that makes certain requirements and recommendations with respect to the construction of extensive green roofs. In this study, we've looked at 4 particular design variables. We're examining the growing media composition with a current recommendation that follows the German FLL guidelines. We're also looking at the growing media depth, which is a requirement of a minimum of 10 centimeters. We're looking at irrigation and also planting as the variables. And it's important to say that while the bylaw requires the construction of green roofs, it does not actually specify environmental performance metrics, with the exception of percent cover of plant cover, which is 80% within the first 2 years. So our overall goals were to evaluate the environmental performance against current construction requirements and recommendations, compare alternative materials and configurations, and make recommendations for performance optimization of green roofs. Now, with respect to environmental performance metrics, there are three key issues. The first concerns stormwater management, and this is an image of July 13th, 2013 in Toronto. In Toronto, similarly to many older cities in North America, suffers from what Christopher Hume calls a 1-2 punch, a combination of aging infrastructure and increase of climate change and extreme climate events. In many areas in downtown, combined storm sewer is still in place, and in parallel, the increase of urbanization results in loss of ecosystem services, including water infiltration. The second performance issue has to do with urban heat island effect, which in turn affects energy usage for cooling in the summertime and contributes to climate change. And the third has to do with the loss of ecologically valuable areas that include vegetation and soil, thus decreasing the ecosystem functions, including cooling via plant transpiration and biodiversity. The reason that green roofs are applied is for their environmental mitigation capacity. And here we're looking at the capacity to retain stormwater and reduce or delay the peak flow of storms. So with respect to retention, the idea is that the growing media stores the water in its substrate, and then the water is either lost through evapotranspiration, or it's temporarily detained and then released slowly post a storm, allowing for that a reduction and delay in the peak of the storm. The other performance has to do with thermal cooling, where we have evaporation through the soil and transpiration through the plants, and also the surface of the plants provide with a more reflective surface than, let's say, conventional blacktop roofs. And the third is the provision of habitat, looking at the kind of increasing loss of vegetated areas in urban areas. Green roofs provide with plant cover and biodiversity, and as well as seasonal variety and potential for species habitat. So the kind of experimental setup looks like this. We're looking at 3 performance criteria, 4 design variables, and the alternatives are the FLL compliant, which is the recommendation from the city, and an alternative, which is a biologically derived or compost-based with a high organic content growing media. The growing media depth is 10 centimeters, which is the requirement. 15 centimeters is the top range of extensive green roofs, and so we want to look at whether that additional depth will increase performance. Irrigation, the 2 main practices are no irrigation and timed irrigation or daily irrigation, and we're looking at a third option, which is a soil moisture sensor activated irrigation. And then with respect to planting, the go-to plant and the recommendation also from the city are sedum mats, and here we're looking at an alternative of grass and flowering plants mix. Now, why these particular alternative comparisons? The industry practices in Southern Ontario divide into 2 camps, particularly with respect to the subject of organic content in growing media. Those who state that organics will biodegrade, lose porosity, and become waterlogged. And those who disagree with these claims and instead maintain that higher percentage of organics supports a range of vascular plants such as grasses and forbs, as well as sedum, while also providing with higher water retention capacity. The mineral-based media that you see down on the left complies with the FLL guideline and is recommended by the City of Toronto in the Green Roof Construction Standard. It contains a high percentage of lightweight expanded aggregate and a very low percentage of organic matter, and is designed to be very free draining. The organic that you can see on the bottom right consists primarily of pine bark compost and contains a very high percentage of organic content. Each of these growing media were tested at 10 centimeters and 15 centimeter depth, 10 centimeters being the minimum required. And here in the graph you can see the kind of test for water retention capacity between the two different substrate, the FLL and the organic media. The choice of vegetation is also an area that has received much attention, with sedum species supplied as pre-grown mass, as seen in this image, are the go-to plants due to their resilience to a broad range of harsh growing conditions, as well as due to the ease of installation. However, there's been much interest in both in research and in practice to include a broad range of plant types for both ecological and aesthetic reasons. The meadow mix, we dubbed it the meadow mix, was selected based on success on other green roof projects in the city, and consists of 16 perennial and annual meadowlands, grasses and forbs that are native to southern Ontario. The mix, which was sown on site, contains bunch grasses, sod forming, and tall grasses, as well as creeping forbs and tall forbs. There are also two opposing opinions and practices concerning irrigation. Some projects employ supplemental irrigation to support the growth and survival of plants and to prevent desiccation and potential fire. On the other hand, LEED gives points for projects that do not use potable water for irrigation, and so many projects can be found to have no irrigation system in place. Of course, irrigation also becomes a cost issue. To date, no studies have examined the potential use of soil moisture activated irrigation as a means to balance water availability for plants and water conservation. So as mentioned earlier, our experimental setup consists of 33 test modules in a randomized layout. Each testing module, roughly 4 by 8 feet, consists of a waterproof membrane, a drainage layer, a geotextile filter, planting media, and vegetation, which essentially emulates a typical construction of a green roof. And in our case, the modules are suspended off the roof deck to accommodate for various sensor instrumentation, particularly runoff capture. So I'd like to share with you a few of our research findings to date. The first is a study which was led by our biology coordinator, Scott McIver, and took place between 2011 and 2012, and focused on correlating plant growth, meaning cover and diversity, with respect to the growing conditions, namely the growing media and irrigation. The vegetative cover measure by percent cover is commonly used measure of green roofs when investigating performance. And as mentioned, the City of Toronto requires an 80% cover within the first 2 years. And as mentioned, sedum species have been studied at great length in various climate regions, while grasses and forbs to a lesser extent. And since many non-sedum plants are being tested and specified in North American extensive roofs, there is an increasing interest in augmenting the organic content of extensive green roof growing media to support a broader range of vascular plants. So to collect vegetative cover data, we use a point intercept method with a pin frame to quantify the proportion of pins touches out of 16 in total. And then in the meadow mix, plant diversity was measured by haphazardly setting a 30 by 30 centimeter square sampling frame in each module, then counting species richness and abundance, from which a species diversity index was calculated. For the sedum, however, we looked at growth form differences between the cultivars, those with broad leaf, sedum spurium, for instance, cylindrical leaf, sedum album, or rigid leaf, such as sedum acre. In the grass forb plant combination, modules with organic growing media had significantly greater vegetation cover than the FLL base module. And here I'm using our green roof image index to show some of those differences side by side, where these are some of the FLL mixtures. These are the organic media. And this is, again, with respect to the kind of grass and forb mix. Those that have the more sparse vegetation have no irrigation. So in the FLL media, having no irrigation resulted in considerably less cover than all combinations, and you can see that drop right here in the second summer around July. Above ground biomass was also significantly greater in organic-based growing media in both grasses and forbs compared with the FLL-based growing media after 2 growing seasons. And no significant effect of supplemental irrigation was recorded despite above ground biomass being less in non-irrigated modules, especially in FLL growing media. And lastly, declining cover was anticipated to follow in successive years. So you can see here from the images the FLL media with the meadow planting, with the FLL and no irrigation being the worst combination. And this was an image by sliding the scale to actually this summer, July 2015, to see whether our assumption was correct about declining cover. And in fact, the results are quite the same. And conversely, this is an image from the same date, July 2015, looking at the organic media with relationship to the grass and meadow combination, and showing how the cover was much greater than in the FLL media, with the exception of in some cases where irrigation is not employed. So supplemental irrigation had a significantly positive effect on plant species diversity in both FLL and organic-based growing media, but no difference between the 2 treatments of irrigation, the timed irrigation and the soil moisture sensor irrigation. So when irrigated, both the FLL and organic growing media treatments were similarly species rich by the end of the 2nd growing season, but plants were larger and more abundant in the organic-based treatment. And these images above show both the organic beds on the left here and on the right with no irrigation, and the FLL in the middle. So with no irrigation, all meadow plant species in August and September, except for 2 warm season grasses, Bacilla carpendula and Bacilla gracilis, and to a lesser extent Festuca rubra, all the species essentially died or disappeared. And in fact, these the perennial grasses that remained are typically recommended for green roof installation due to their drought tolerance. But as you can see here, the species diversity dropped quite a bit. We are not seeing any of the flowering plants, and we're left with essentially a couple of different grass species. Fast forwarding to 2015, we're seeing that not only is the plant cover and diversity remains the same as in 2012, but what we're also seeing is that the loss of vegetative cover and root mass results in erosion and loss of soil due to wind scour. As a kind of side note, and this is an article that our biologist Scott McIver published in Living Architecture Monitor, looking at several other winners, let's say, that are also resilient to drought and also provide different other amenities such as habitat for pollinators. And those are two species, evening primrose and blazing star, that are part of the mix on our roof. The sedum plant modules exhibited very little change in cover as a result of growing media type or supplemental irrigation regime. And so if you can compare the drop from 100 to 0% in the meadow, where in some beds we actually reached 0% cover, the meadow pretty much remains within the top 90% of cover, which is within the requirements of the City of Toronto Green Roof Standard. However, biomass was significantly less in the FLL modules, and you can note the kind of difference. Well, it's hard to see from a kind of aerial image, but some of the images, some of the modules that have no irrigation, particularly with the FLL mix, the biomass decreased. Moreover, the assemblage of sedum morphotypes, as I mentioned, the broadleaf, rigid leaf, and cylindrical leaf, did shift over the course of the 2 years. The broadleaf sedum species were significantly more abundant in organic media, and you can see that with the green color, while cylindrical leaf sedum were significantly more abundant in the FLL media. So over the years, we've observed that although sedum maintains a very high cover, cover biomass and cultivar types decrease when planted in FLL media. And you can actually, this is taken from July 2015, seeing how vegetation has evolved over time, and you can note some of the patchiness that begins to occur with the FLL media, and particularly with the no irrigation, as opposed to the organic media, irregardless of irrigation. I should also mention that this study confirms and quantifies the kind of observations by green roof growers in Toronto. And finally, several studies have demonstrated that combining both sedum and non-sedum plants rather than focusing on one or the other, which our study currently looks at, is likely to improve green roof performance, and this could be one of the research directions that we would pursue. So overall, the conclusions from this particular study are looking at plant cover and above ground biomass in meadow and sedum. Green roof is significantly less after 2 years when industry standard FLL growing media are specified. Meadow planting diversity is unaffected by growing media, but highly dependent on supplemental irrigation. Different sedum growth forms dominate depending on growing media specifications, and overall growing media and irrigation impact vegetative assemblages differently and somewhat independently. The second study that we just completed looks at the thermal performance of green roof and the relative influence of 4 design variables on thermal cooling. And this study was also led by Scott McIver. As in the previous study, we looked at vegetative cover structure sampling using the pin frame, and we did those over the 2 years with 13 different sampling times. To measure the thermal data, 5 sensors were installed along a vertical center axis to generate a thermal profile for each module. There was one that was at the underneath the bed, one at the base of the growing media, one just at the surface of the growing media, 6 inches above the growing media, and 60 centimeters above the growing media. The temperature was then subset by daylight hours only, and the mean, max, and minimum were determined for each day of the sampling week, then compared to one another. Overall, plant cover and structure were significantly correlated, and you can see here with beds that have a lot of cover also had showed a lot of structure or height. Modules with greatest vegetation cover included sedum planting and organic soil, with irrigation having no effect. So you can see here the irrigation not really playing a role, but the best performer is the organic and sedum. This bed has the FLL and no irrigation, and this one has the organic and timed irrigation or daily irrigation. Irrigated meadow planting in organic substrate had significantly higher vegetation structure, and you can see that from this particular diagram. And just like in the first study, here we saw once again that the effect of irrigation was most notable in meadow mixture that suffered 2.6 times decrease in cover and 2.7 times decrease in structure in the FLL mix. The effects were less pronounced in the organic substrate, with meadow mix declining in structure and cover by only 1.4 times and 1.6 without irrigation. And cover and structure in sedum planting was unaffected by irrigation. So our analysis shows that there were significant differences in temperature recorded at all sensor heights among the green roof modules. We found an average of 2-degree difference at sensor C, which is right at the surface of the planting bed, and a 1.5 difference at sensor D, 15 centimeters above the planting bed. And those are differences between the hottest treatment combinations, which are meadow, FLL with no irrigation, shown on the right, and the coolest combination, sedum, organic, and irrigation. Now, the difference between the maximum temperatures, so those were the averages, the 2 and the 1.5, but the maximum temperatures reach a difference between 8 degrees between the hottest and the coolest, and then in level C, and then 5 degrees between the hottest and the coolest in level D. So the greatest effect size among all variables came from planting type, where sedum outperformed the meadow species. However, one exception was that irrigated meadow in organic media performed as well as unirrigated sedum in FLL media. So in conclusion, for this study, the modules receiving supplemental irrigation had roof temperatures that were significantly cooler than non-irrigated modules. Plant structure, not cover, greater in meadow planting than sedum over 4 years. Roof cooling is not significantly reduced with plant structure. Cover is more important. Roof is cooled more with sedum than with meadow planting, regardless of growing media and irrigation. And the top performing combination included irrigation sedum planted in either depths in the organic substrate. Now, determining the cooling potentials of individual plants and of different species could help develop models for planning supercooling green roof plants communities. In other words, in our study, we looked at the plants as a community and not for individual plants. So, for instance, some studies have found that, for instance, lamb's ear outperforms sedum in cooling due to its reflective white hairs that dissipate solar radiation, so, which means that there's potential to look at individual plants as high-performing cooling plants. And again, in this study, it is important to mention that we're looking at these two planting communities in isolation, but that the potential of actually mixing sedum and meadow planting also offers a viable solution. The last study that I'll share with you, which is currently in preparation, was led by Jenny Hill, a PhD candidate in civil engineering, and focuses on stormwater management, volumetric runoff calculations, and peak runoff coefficients. The study analyzes 176 storms and between 2013 and 2014, where 2013 was a much wetter year, which certainly plays a role in the overall analysis. Precipitation was recorded via our weather station on site. Now, the growing media moisture content was recorded with a soil moisture sensor, seen on the left, and runoff or discharge from each test bed was measured with a rain gauge or tipping bucket. It is important to note that in 2013, the beds that were irrigated received 5 minutes of irrigation daily, and in 2014, this was reduced to 2 minutes per day. And this is the irrigation system that we have, a standard drip irrigation system. And the last sort of variable in the water balance and in the kind of study that we have also integrates an on-demand option, which is instrumented with a soil moisture sensor to control irrigation based on the level of soil moisture in the soil. So our findings shows that the relative effect of 4 design factors on volumetric runoff were analyzed here using a stepwise regression, producing this regression tree that you're seeing here. And at each level, the mean of the beds that are calculated or analyzed are shown. So these are averages of the beds. This technique identifies a single factor which provides the greatest difference in group means and classifies the data accordingly. This continues through successive branches until no significant difference in the group means can be elucidated. So in 2013, the most dominant factor was irrigation, as you can see here. The modules that received 5-minute daily irrigation discharge over 80% of the precipitation volume and retain less than 20%. The modules that received no irrigation retained twice as much. The modules that were assigned the moisture sensor irrigation reduced discharge rate to 68%, so a kind of happy medium. And in combination with the organic growing media, it was reduced down to 59%. Now in 2014, the reduction in irrigation from 5 to 2 minutes made a significant difference in the runoff volume from 82% to 51%. So this is the retention. And from 68% to 44% with the soil moisture control irrigation. And of course, as I mentioned before, this change also reflects the fact that 2014 was a much drier year than 2013. And again, the organic media plays a significant role in increasing stormwater retention. However, the growing media does not make a significant difference in the modules that do not receive irrigation. In fact, no other design factor, growing media type, nor depth, nor choice of vegetation, significantly influence the hydrological performance. So really, irrigation is the most significant factor for stormwater retention. So with no supplemental irrigation, an extensive green roof can retain between 60 and 70% of the annual precipitation. And conversely, if the roof is irrigated successively or daily, the annual stormwater retention can drop down to less than 20%. Now, another key finding of this study is that if the growing media is already moist, the most influential variable is the choice of growing media. And you can see that in this particular diagram. The organic media outperformed the mineral-based media by as much as 4 times when fully saturated. In other words, organic retaining 83% and FLL media 29%. Therefore, for stormwater management, the worst combination would be the mineral-based or FLL-based media with daily irrigation. And although plant cover did not play a significant role among the 2 plants, the sedum species outperform the meadow. One possible explanation for this is that the function of interception of precipitation. In other words, the cup-like leaves and waxy surface of the sedum canopy captures the rain, which in turn evaporates directly off of the surface as opposed to infiltrating the soil and cycling through the soil and the plants via evaporation and transpiration. Now, another critical finding in this study is a dramatic difference between the peak runoff coefficient that is currently locally practiced, which is 0.5 or 50% retention, refers to as pre-development state, versus the peak runoff coefficient that was calculated in this study, 0.1 to 1.5 or 85 to 90% retention. The former is based on the FLL guidelines and the latter is based on empirical data that was derived in this study. So 2 critical points that follow from this. First, with this new recommended runoff coefficient, a minimum of coverage of 60% of the building footprint with an extensive green roof would improve stormwater capture beyond the pre-development state and would require no other management infrastructure such as cisterns or any other infrastructure on site, thus reducing construction costs and freeing up valuable land for other usages. Secondly, the Toronto Green Roof bylaw currently requires only a minimum of 20% coverage, which means that the developments that meet this minimum requirement would fail to capitalize on the runoff reduction potential of an extensive green roof and would require additional stormwater infrastructure management on site. Overall, the conclusions from this particular study were that irrigation had the largest overall impact on hydrological parameters. The soil moisture sensor controlled irrigation improves these figures somewhat, as did the use of organic growing media. This wood compost-based medium reduced the runoff coefficient, particularly when events occurred in already wet green roof, whether it's due to a previous storm or irrigation. An extensive green roof optimized for stormwater management in southern Ontario would then comprise a high organic growing media, either with sedum species and no irrigation, or with native meadow species with soil moisture sensor controlled irrigation. The other important finding is the 0.1 or 0.15 peak runoff coefficient, and that should replace the currently practiced 0.5 coefficient. And then lastly, green roof bylaw should increase the minimum required extensive green roof coverage to optimize stormwater capture via green roof. Now, in this discussion, what I'd like to do is look at how the three different studies perhaps overlap and come together, and what kind of conclusion we can draw from some overlaps between those studies and where those studies diverge. Overall, organic growing media has shown to outperform the FLL for stormwater management, thermal cooling, and plant growth, particularly for meadow mix. Irrigation was the most significant factor for all three performance criteria, but in opposing ways. On-demand irrigation using a soil moisture sensor proves to be a good compromise, particularly when used in combination with organic media, which has a higher water retention capacity. Sedum species is certainly proved to be a top performer for both stormwater management and thermal cooling. And we believe that leaf interception may be at play here. And non-sedum plants such as grasses and forbs offer other important aesthetic and ecological benefits, and so should not be precluded from plant specification. And so optimizing plant performance could be achieved by actually combining sedum and meadow species. And on that note, a study that Scott McIver conducted at the Grit Lab looked at the relationship between plant communities and pollinators, which are an incredibly important factor in biodiversity, food availability, agricultural pollination, and so on. In his study, he found that the proportion of sedum pollen in the pollen loads of foraging bees collected was high amongst all bees, average 80.5% of total pollen load, but significantly greater for exotic bees compared to native bees. Conversely, native bees had significantly greater number of non-sedum pollen types, comprising more than 20% of their pollen loads, meaning these bees might be visiting flowers at ground level and on the roof in the same foraging bout. Another study that Scott conducted looked at 29 sites in Toronto and relating building heights to bee nesting success. It was found that building heights was negatively correlated with the abundance of brood cells. And you can see here building levels and the number of bee species found on the roof, and positively correlated with the number of unfinished cells. And furthermore, a decline in green roof space area within 600-meter radius around each rooftop resulted in decreasing species richness and abundance. So as roof space and radius or proportion of roof increased, the abundance dropped. Oops, what did I do here? Sorry about that. Oh, okay. So with the reason I bring these studies up is because most new construction nowadays in Toronto actually towers over 20 stories and above. And so plant diversity, species, and species habitat may not be the top priority, while thermal cooling may also not be top priority because of high wind velocity, which would make any sort of microclimate condition essentially negligible. However, in these heights, perhaps stormwater management is prioritized over others. That is simply to say that site matters, and that each green roof should really be prioritized according to geographic, local site conditions, and building type. We also, what comes out of the studies is that new recommendations for the peak runoff coefficient and minimum green roof coverage to maximize stormwater capture should be reevaluated in the City of Toronto Green Roof Bylaw and construction standard. And finally, that it is necessary to establish performance benchmarks that are evidence-based and continue to improve them through ongoing monitoring, particularly with respect to different site conditions, ecological dynamics such as plant succession, and changing climate patterns. And with that, I'll conclude my presentation and will invite you to ask any questions or make suggestions. Thank you.
I have two questions. One is, what is the weight load difference between organic and the FLL growing media? And is there any empirical data on using on-demand irrigation using gray water?
Two excellent questions. I don't have the answer to your first question. I can find that data, and maybe we can I'll get that to you later. But load would definitely be one aspect that we would consider as a kind of next study in terms of looking at the overall life cycle of the different configurations. One thing that I sort of neglected to mention was that in terms of, and this doesn't necessarily directly relate to your question, but relates to the overall idea of life cycle assessment and measuring the overall performance of these different configurations, has to do with the fact that the compost-based media, or the biologically derived, is essentially 100% compost. So in terms of embedded energy costs, it's at a plus, where the FLL media is mined and transported, and therefore has a much higher embedded energy cost. So in addition to the load, if looking at the kind of life cycle assessment, also the origins and production of the media would be part of it, and that's something that we haven't gotten to yet, but it's on our plans. With respect to gray water, Again, I don't know of any specific studies offhand that have looked at gray water recycling, but this is something that we actually have plans for our next site, which would be on the rooftop of the one Spadina new building location for Daniels, comparing not necessarily gray water as in cycling from the building, but looking at rainwater harvesting, which certainly has a lot of potential as gray water reuse, and comparing that to potable rainwater as sources of irrigation, looking at both quantity and if captured through a cistern and then cycled, and then also looking at quality.
Here, why intensive roof was ignored from your studies?
Sorry again?
Why intensive roof was ignored from your study? That's one question. And the other, we all know bees fly only within 10 feet from the floor. So how you expect them to go on roofs?
It's a good point. I guess I'll start with your last question first. Well, first, you know, we have our bee expert here, Scott, in the audience, so maybe I can have you talk to him directly. But one of the key issues with respect to green roof performance is that the overall sort of perception or idea of green roof performance is that all green roofs function in the same manner for all performance criteria, regardless of where they are located. And so one of the things that we are trying to look at is, with respect to the current construction that is happening locally, and being that the green roof bylaw is mainly is specified for new construction, and that mainly new construction above 2,000 square meters is high rises. The question is, are green roofs effective in terms of bee habitat, which is one of the kind of item lists of green roofs performance that you will see listed. Green roofs can do this, 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 and that, about a list of about 20 different things. And so one of the key aspects is to really quantify these statements and empirically prove whether they are or not effective, or effective or not effective, and if they are, how effective are they? So to answer your question, perhaps it is a kind of obvious, but it is one of the sort of items in terms of species, habitat, and pollinators that green roofs address, and this study clearly shows that building heights matter to the presence of bees. And the sort of the point that I'm making is that perhaps in designing green roofs, there should be perhaps prioritizations of different performance criteria based on the location, both geographic and local site conditions for each particular green roof, so that in those cases that are where the roof is at 20 stories high and above, perhaps stormwater is really prioritized, in which case species biodiversity of plants may not be as important. And if we know that the sedum function are the winner for stormwater management, that perhaps the sedum is the one that is employed, where in other conditions an argument for plant biodiversity may be more important. And so the take-home message from that is really that designers have the tools or the choice to actually make these, and it's really important that we do so, and we look at all these variables not as a kind of one cut and paste system, but really make these kind of choices based on site and performance criteria. And then your first question was, remind me?
Why you ignored
Oh, the intensive. Well, the first, I mean, strictly in the context of Toronto, the green roof bylaw focuses on extensive green roofs. So we wanted to look at what is the most common practice of green roofs and trying to elucidate what are the current industry practices, what are the standards that the City of Toronto has as part of their construction standards that are then followed in practice. Are they effective? Are there issues or configurations that are more optimal for the kind of climate that we have here in Toronto, particularly with a kind of changing climate and more extreme events and so on? And that the reason that extensive green roofs are selected or legislated or incentivized over intensive roofs in general in many North American cities is because of the load issues and the cost issues, that it's much cheaper, it's a lot more lightweight, and relative to the cost and the weight, the impact for environmental management is quite high. So that is why extensive roofs. Mm-hmm.
Hi, just to exactly your point of the 20-story buildings, this seems like the vegetated wall is a really, good solution. And so can you talk about the experiments you're doing there?
Sure. To date, we are in fact looking at the potential of green facades. Green facades being usually trellis structures with vining plants, as opposed to some other categories such as green walls, where it's, for a lack of a better description, a kind of green roof 90 degrees, which seem to be less viable for a climate like Toronto's climate, and require a lot more maintenance. And also require a lot more load and construction. So the green facades essentially attach to any sort of building facade, whether it's new or a retrofit. So there's an advantage to those kind of structures, and don't actually put a lot of load onto the building envelope. To date, we've looked at the thermal cooling potential of green facades on building envelopes, and what we found is that by midsummer, when vegetative cover reaches about 70%, you can see about 3-degree cooling between vegetative facades and a non-vegetative facade. We've also looked at, and we're repeating this study to look at different kinds of vining plants and different structures, and looking at also from a design standpoint, what are the kind of growth forms of different vining facades. Some tend to grow horizontally, some shoot up, some have a full dieback in the winter time and begin from the ground up. Some leave their stems and the leaves grow from the stems. So we're looking at, from a design point of view, what are the different growth forms of vines and how that correlates to thermal cooling performance. And maybe there's even a potential for combination of different vining plants based on these kind of growth forms. We haven't looked at the relationship between vining plants and pollinators or any other species. For instance, many other vining plants could be specified that have that fruit, for instance, that could provide food for different birds and so on. There could be different flowering vining plants that could provide for pollen and so on. So our work to date has just looked at the thermal performance, because it's something that hasn't been really quantified in this particular climate region, and specifically in Toronto. The City of Toronto is looking at at this as an option, not necessarily as a kind of requirement, but perhaps as a guideline for outfitting building envelopes. So our recommendation would be for these green facades, and thermal performance would be one of the key sort of aspects that the city would be looking for in terms of the environmental sort of argument. I hope that answered your question.
And I wonder at some point if it really should be considered a vegetative roof or something like that, or a vegetative facade. You know, green roofs, when you go to Parliament Hill, they're green because of the patination on the copper. Or if you talk to some manufacturers, they feel that a green roof is because their products have something sustainable about them. And the new CSA standard for wind load uplift addresses vegetative roofs and non-vegetative roofs. It's almost time. You've probably had a discussion at some point about what we call these things.
Yeah, it's a very good point. I think the nomenclature has stuck because it's been something that has that has been discussed so commonly. Not only in North America. I mean, the green roofs really began in Europe, and then made their way over here about 30 years ago. And the industry sort of the industry dubbed it green roofs, and so the kind of nomenclature has really stuck as the terminology. But you're absolutely correct. The differentiation is important because we are talking about vegetated roofs. There are probably other kind of technologies that could perform a lot of these performances, like stormwater retention, that are not vegetated. Or there's always the argument of a high reflective white roof with the green roof for in terms of energy and temperature reduction. And so I think that you're right by differentiating the fact that it is a vegetative roof. That is a really important component, specifically from an ecological standpoint and also from an aesthetic standpoint.
Yeah, hi. I just had one question that came up as a result of your answers a second ago, and another question which I'd been wondering about. So first of all, I was wondering, it looked like you were doing some studies with photovoltaic panels over the vegetated roof.
Correct.
Was that something you were presenting? You're going to get, or is that something? And then the other question was the 3-degree difference in temperature when you had a vegetated wall. Was that was there an aspect of that was contributed, that was an effect of the vegetation, or was it simply the shadow on the wall?
So to answer your second question, the 3-degree cooling was the effect of vegetation on the facade. So even in the control areas where we had no vegetation, the trellis was still there. So any sort of shadow effect would basically be equal to the two. So we're looking at the surface temperature of the control area, the non-vegetated area.
Well, would a full shadow affect? A trellis is one thing, but that's not going to give as much shadow as a green climbing
right
wall.
And so your question, yeah, your question is still valid in terms of quantifying, let's say, the effect of transpiration versus shade. I guess that's something that we could certainly look at is what are the kind of actual transpiration of leaves versus, let's say, if you put a non-vegetated, a non-vegetated screen of some sort. But the other argument would be that there's a kind of multifunctional aspect to vining, to plants, in terms of their aesthetic quality, in terms of perhaps, habitat, the resources, and so on. So there's other there are other considerations, I would say, that as a kind of holistic design approach that are not just about the kind of the thermal performance. But your question is valid in terms of comparing whether it's the effect of the actual leaf and the vegetation, or whether it's something that would just be would be an effect of any sort of a screen or a shade. And the project that I showed with the combined green roof and solar, we have just recently constructed, so I don't have any data to share with you. So this would be something that we would probably be ready to do in about a year or so. And we will continue to update our website, which is listed here with our publications. So stay tuned for an update on some of our findings, both with respect to energy efficiency as well as plant growth and water management.